Hello, Gen Chem 2 class. This is the online lecture for today. This is Dr. Rowley on February the 3rd. I'm going to let's see, I'm going to try to change the window over to, there we go, the screen. And this is, I hope this is recording okay, no guarantees. And if it doesn't work, this is my second try. We'll see what happens. All right, so day 2, Gen Chem 2. For the announcements, don't forget that there's a quiz on Friday. I have set it up. I'm trying to remember now because I did it a few hours ago. It is a quiz that will be available for 5 minutes. And you're going to need to take it sometime during the day on Friday. Sometime between, I believe, 8 and 5 on Friday, you'll need to take the quiz. Make sure you'll have 5 minutes to take it once you log in. Worksheet 1 is on Moodle as an assignment. So what you need to do is download that worksheet and then work it through, and then either take a photo of it with your phone and upload it to Moodle as a PDF, or you can scan it and upload it as a PDF. So there are several ways to convert documents into a PDF. There is an app that Adobe has on both the Android and Apple services, the app stores, that you can download for Adobe to convert. It's a converter to a PDFs. You'll need to upload your files for worksheets as PDFs each time. All right. By the way, also, it was good to get to chat with many of you over the last 2 days. I think there's 2 or 3 more that I need to chat with yet, but it's been good to meet you. Yeah, so here's the announcements. The quiz, the worksheet is due Thursday at midnight, and don't forget Lab 1 next week. All right, I'm going to start today with a little bit of review from what we did on Monday with solutions. So chapter 13, as we talk about solutions, we emphasized the solute and the solvent equal the solution. This is very simplistic. This is critical to what we're going to be doing later in class today. Remember that the solute, what is dissolved? The solvent does the dissolving. It's often a liquid. The solute, for our purposes, will typically be a liquid or a solid. The solvent is a liquid, and then the solution is a combination of both. Treat these as 3 separate things. Excuse me. I talked about the process of how salts dissolve on Monday. I'm bringing this back because this is critical to what we're going to be talking about today. So here we have a chloride ion, a negatively charged chloride ion, surrounded by 6 water molecules that have all oriented their positively polarized hydrogen ends toward that chloride. They surround it, they carry it off into solution, and that's how salts dissolve. Here we have a positively charged sodium cation. The negative end of the polar water molecules orient themselves toward it. 6 water molecules on average solvate every sodium ion. Electrolytes. So what I want to talk about now with regard to electrolytes is salts. Let's talk about salts. They either dissolve or they don't. But let me back up. An electrolyte solution is simply a solution that has dissolved ions. So the previous slide where you saw the process of... Excuse me. You know, that same thing happened when I was trying to record this before. One of my Medtronic colleagues called me right in the middle of it, and when I tried to pause it, I started over. So I'll have to call my wife back. Anyway, so the electrolytes, dissolved ions. Think about that as dissolved ions. The greater the number of dissolved ions, the greater the electrolyte strength. Strong electrolytes is where you have compounds that completely separate as ions in solution. Things that are weak electrolytes only partially dissociate. Things that don't produce any ions at all are non-electrolytes. So think about that in terms of amount of ions dissolved. Now, let's talk about ionic salts. We have an ionic compound. We'll talk about how soluble they are in a minute. Ionic compounds, they either dissolve or they don't. So if an ionic compound dissolves, and let me go back and review a couple of things. Remember the things you need to memorize. Not a lot, but there are some things you've got to absolutely know. And the first one is your ion sheet. List of cations, list of anions. Make sure that you know those. That's number one. Number two, you need to know the metric prefixes from chapter 1. You need to know those, metric prefixes. I'm assuming that you know them and can work with them pretty fluidly. The third thing you need to know are your solubility rules. We'll talk about those in just a moment. The solubility rules determine whether a salt will dissolve in water or not. If a salt dissolves in water, strong electrolyte, because it dissolves by separating into individual ions that distribute themselves throughout the solution. If a salt does not dissolve in water, it's a non-electrolyte because all of those ions are hanging together. So for salts, if they dissolve, strong electrolytes. If they're not soluble, non-electrolytes. It's either strong or non for salts. In the case of acids, you know that acids, if you look at your ion sheet, look at the list of anions. An acid is anything where hydrogen is the only cation. Pick an anion, chloride. Add a hydrogen ion, HCl, hydrochloric acid. We'll talk about acids a little bit further down the road. Review that part of Gen Chem 1, where it talks about acids and bases. So I've already talked about 3 things you need to memorize: ion list, metric prefixes, solubility rules. The 4th thing is you need to know your 7 strong acids. Your 7 strong acids. These are the 7 strong acids: HCl, HBr, HI, the 3 hydrohalic acids: hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, perchloric, and chloric. So these are the 7 strong acids. Notice that hydrogen's the only cation in each case. Now, with acids, remember with salts, they either dissolve or they don't. In the case of acids, all acids dissolve. All of them dissolve. They're all soluble in water. But these are the only 7 that totally separate into their cations. So HCl totally separates as H plus and Cl minus in water. HBr, HI, HNO3, H2SO4, 2 hydrogens and 1 sulfate. Total separation into their cation and anion. These are strong electrolytes. These are strong acids. Every other acid is weak. Every other acid is weak. Remember, all acids dissolve. These 7 totally separate into cation, anion. Everything else stays together. Now, what that means is something like this. Let's pick HF. HF is a weak acid. It's not one of the 7 strong ones. So what that means then is that when this dissolves in water, but the hydrogen and fluorine are kind of tightly bonded together. Maybe 1% of the molecules actually dissociate. So maybe 1 out of 100. So when that happens, you get some ionization, but not much. That's what happens with almost all acids. They're weak. They dissolve, they don't separate into a lot of ions. So salts, they either dissolve, strong electrolytes, or they don't, non-electrolytes. For acids, they all dissolve. They either separate, strong acids, or they don't separate so much, weak acids. So keep that in mind as we move forward. Let's review the solubility rules. This is number 3 of the list of things to memorize. Solubility of ionic salts. These are listed on page 30 in your text. So if you've got your textbook in front of you, as I'm sure you all do, make sure that you turn to page 360 and follow along. First of all, we've got these 4 anions. Whenever these 4 anions are part of a compound, that compound will always be soluble in water. We're talking about solubility, it's always solubility in water. Any nitrate, any chlorate, any perchlorate, any acetate. These 4 ions, you've got to recognize them. This is why you have to know what the names and formulas are. This has to become second nature to you. So, recognize acetate. You see it in a compound, immediately it's soluble. I would urge you to write this down. So in your notes, please write down these solubility rules. When you write them down by hand, that's an added layer of memory that you're actually giving yourself. So please make sure you write these down. NO3 minus, ClO3 minus, ClO4 minus, C2H3O2 minus. The second solubility rule. These cations are always soluble. These are the alkali metal cations, the group 1 metal cations, lithium through cesium and ammonium. Ammonium ion is about the same size and charge density as potassium. So their chemistries are very, very similar. So all of these +1 cations, their compounds are always soluble, no exceptions. No exceptions to rules 1 and 2. Did you write those down? If not, make sure you pause this video and then go ahead and finish it. Number 3, these 3 halides are always soluble. Their compounds are always soluble. Their salts are always soluble. So if you've got magnesium chloride, magnesium bromide, magnesium iodide, they're all soluble. But now for the first time, we run into some exceptions. For silver, lead, and mercury 1, those salts are not soluble. Any chloride, bromide, or iodide with silver 1, lead 2, or mercury 1. Mercury 1's a weird thing. Mercury 1 is 2 Hg atoms stuck together, and together they carry a +2 charge. So the net charge for each mercury is +1. That's why we call it mercury 1. And by the way, you will never see mercury in lab. You won't see it here at Bethel, because these compounds are very dangerous, they're very toxic. And even liquid mercury, we are a mercury-free campus because no mercury at all. It was about 15 years ago when, let me point out, so in a thermostat, if you've ever pulled the cover off a thermostat, especially the old style ones, it's usually a coil of wire, and on the end, you've got a mercury bulb, a glass bulb with mercury in it. So as that coil heats or warms, that you can adjust to where that switch turns on or off, your furnace. Well, those are the old times thermostats that they had in Heritage Hall. Some guys were throwing a football around, and it broke the thermostat that broke the mercury bulb. Mercury, that little bit of mercury came out, fell into the carpet. They had to evacuate the building, and it cost about $10,000 to remediate that mercury spill. It is not a trivial matter. Now, way back 250 years ago when I was in high school, we used to play with mercury. We used to have liquid mercury that we would kind of push around on the tabletop, and you've probably heard your parents and grandparents and great-great-grandparents talking about how much fun they had with mercury. Liquid mercury itself is not dangerous. In fact, liquid mercury, the Romans used to drink liquid mercury in ancient times as a laxative. And apparently it was effective. That's the one experiment I'm not willing to try. At least I've never had to, so let's hope not. But it is the mercury vapor. So any liquid has a little bit of vapor that comes off of it. that mercury vapor is carcinogenic, so you don't want to be breathing that. That's the dangerous part. All right, so anyway, that's mercury 1. These 3 anions are always soluble unless they're paired up with one of these 3 cations. Let's keep moving through this. Number 4. Sulfates. Sulfates are always soluble, except now we have 6 cations. Notice, so you look at a compound that has sulfate in it, your first reaction should be soluble, unless it's one of these 6. Notice the first 3. Those look familiar? Well, they're the same ones as for the 3 halides. In addition to these 3, calcium, strontium, and barium in the periodic table, these 3 group 2 metals, these 3 alkaline earth metal cations, they are insoluble with sulfates. Last, the 5th and last solubility rule, these anions are generally insoluble with any cation. They're generally insoluble. Now, that's not strictly true. It's not strictly true, because if these anions are paired up with any of these, those compounds are soluble. There are no exceptions to these 2 rules. So, if you've got any of these hooked up with a group 1, group 2 metal, or group 1 metal cation, rule number 2, soluble. Okay. If you have all these written down, I've given you plenty of time. Let's go through some practice. Let's do kind of a speed round here. So identify whether they're soluble or not. First of all, let's practice their names. Right here. Calcium carbonate. Compound is calcium carbonate. If you were to write this, calcium space carbonate. Soluble or insoluble? Quickly. All right, I heard insoluble, and that is correct. Carbonates are insoluble. This is not one of those soluble cations, insoluble. NaOH, soluble or insoluble? Soluble. It's soluble because of Na. Even though this is in rule number 5 is insoluble, rule number 2, any sodium ion, always soluble. You keep in mind there are exceptions to every rule. We're not worried about exceptions right now. We want to focus on the major trends. We're not going to give you screwball exceptions, well, unless we really need to. We've talked about giving you all the exceptions that you'll need to know. Okay, soluble or insoluble? Soluble because sulfate is soluble. This is not one of the insoluble sulfates. It is not zinc, strontium, barium, silver 1, mercury 1, or lead 2. Soluble or insoluble? That's right.
Cindy Raleigh.
Come on, Cindy, I'll call you back. Hey. Good, I'm recording a lecture. Can I call you back? Okay, all right, bye. Sorry about that. That's twice in one lecture, we'll see. So this is soluble. Phosphates are normally insoluble, but the lithium presence, always soluble. Soluble or insoluble? Of course, acetates are always soluble. Doesn't matter what's hooked up with it. Also soluble because of nitrate. Doesn't matter what the cation is. We know that a lot of silver compounds are insoluble. Doesn't matter, nitrates are always soluble. This is why you have to know those cations and anions, folks. You have to know them, you have to be able to quickly recall them, know their names and formulas. Soluble or insoluble? Insoluble. Lead to bromide. Bromides are usually soluble. Lead 2 is one of the exceptions. Chromium 3, Roman numerals closed up to chromium. Chromium 3, that's the cation, hydroxide. And of course, this is insoluble because hydroxides are generally insoluble. Soluble or insoluble? Go ahead, look at your notes. It's okay. This is open notes. This is going to be soluble. Bromides, chlorides, iodides, generally soluble. Soluble or insoluble? Sulfates are soluble, but barium's an exception. So barium sulfate is insoluble. Soluble or insoluble? Of course, all potassium salts are soluble. K2CrO4 is soluble. What about Hg2NO3? Nitrates, soluble. Nitrate, soluble. Iodides, soluble, but mercury is an exception. And then finally, well, next, this, soluble or insoluble? Titanium 4 sulfate. Sulfates are soluble. Titanium's not an exception. Soluble. Ammonium sulfide. Soluble because of ammonium. Soluble because of perchlorate. Okay, I am going to try to, there we go. See if I can do this. Perfect. Okay, now let me see if I can, yeah, I need to have, all right. Net ionic equations. Okay, just tried a little experiment there and it didn't work. Okay, let's do a quick review on net ionic equations. For net ionic equations, what you do is you have a molecular equation. Now that you know your solubility rules, if I were to give you a compound, you should be able to tell me what the form of it is. Is it AQ? Is it S? Is it L or G? Which state of matter is it? Aqueous, solid, liquid, or gas? Right now, we're just looking at solids and aqueous. Is it soluble or is it not? So here is an example of an overall molecular reaction. AgNO3, you know that it's soluble, AQ. NaCl, you know that it's soluble, AQ. Now, if I were to give you just the way to interpret things from me, the way I do things, if you see Ag plus by itself, it's automatically AQ. I won't put AQ by ions because inherently they're already dissolved in water. AgCl, you know, is a solid, and then NaNO3 is dissolved. So this is not soluble, the other three are. Once you have the molecular equation, we write the full ionic equation. And for full ionic, the only difference here is you do this. Everything that's AQ, you separate it into cation and anion because that's how it actually is in a solution. And this is the full ionic equation here. So we've got Ag plus, NO3, there's a minus here, it's hard to see. NO3 minus, there's a minus here for the Cl. Notice I did not write AQ by any of these ions. But for AgCl, I wrote solid because that indicates its state of matter. Everything that's AQ, you simply spread out into its ions. By the way, be careful if you have something like CaCl2, that would be Ca2 plus and 2 Cl minuses. So if you've got more than one ion in a compound, that becomes the coefficient in the full ionic equation. For the net ionic equation, you look at your full ionic equation, anything that's exactly the same on both sides, subtract out. We have a sodium here, we have a sodium here, we have a nitrate, we have a nitrate. So the net ionic equation looks like this. This is the essential reaction that occurs for net ionic equations. This is Gen Chem 1 review. Now, here's where we get into the meat of chapter 13, solutions. Today, I'm only going to cover concentration units and we're going to work through some examples here. We're going to work through a couple of calculations. Solubility of gases, liquids, and solids. Well, we talked about the solubility rules for solids. We'll talk about gases and liquids on Friday, and we'll talk about colligative properties. So on Friday, we'll be done with most of the topics from chapter 13. Maybe not all, but we'll be pretty close. So the goal for today is to get through here. All right. There are 4 concentration units that you'll have to know. 2 of these you already know. We've worked with these before. So molarity is moles per liter. Moles per liter, by the way, is not good enough. This is moles of solute per liter solution. Okay, this is odd. It's showing up nicely on my screen. You're not really seeing very clearly the orange dividing line here. Moles of solute per liter solution, that's molarity. If I were to ask you for the definition of molarity and you left these parts off, that would not be correct. Make sure that you identify. Remember the very first slide? Solute plus solvent equals solution. Don't ever lose sight of that. That's becoming even more important right now. Moles of solute, liter solution. Mass percent, you know this one too. Part over the whole times 100%. So a percentage is simply a fraction times 100. Let's jump down here to mole fraction. Mole fraction, here we have moles of A, usually moles of solute, over total moles. Part over the whole. Part over the whole with units of moles, but not times 100%. That's why this is a fraction, this is a percent. Notice the Greek letter chi here. The Greek letter chi is the symbol for mole fraction. Yeah, it's a little bit weird. And then finally, molality. Molality. Molality is a lot like molarity. The difference is in the denominator. Instead of liter solution, this is kilograms of solvent. We'll come back on Friday and talk about why we would use molality instead of molarity. Okay, do you have all this written down? Just like the solubility rules, this is important for you to write down. You'll need to know these. And this is why. Concentration conversions. So here we have a problem. You're given two things. You're given a solution. We're given the molarity, and we're given the density. We're given the molarity and the density of a solution. Determine molality, mass percent, and mole fraction of nitric acid. What's the formula for nitric acid? Quickly, come on. Nitric acid. Yep, HNO3, you got it. Okay. So what I'm going to do is walk through how I would solve a problem like this. There are lots of ways to solve it. You may solve it however you like, as long as you get the correct answer. So what I'm going to do is walk through this problem carefully, thoroughly, and then I'm going to talk about the worksheet, worksheet 1, which is posted on Moodle, which you will need to download, write out the answers to, and then upload to Moodle. This is for the assignment. So what do we know? 16.0 molar HNO3, and we know that the density is 1.51 grams per milliliter. Whenever you're given a density, the density always refers to the solution. So here's how I recommend, I set these problems up. If you want to follow this, great. If not, that's up to you. Grams, moles, and volume. And I'm going to start with solute, which here is HNO3. Then we have solvent, which is H2O, because water is always our solvent here. And then finally, the solution, which is the combination of the two. All right, I hope you can see this okay. I'm going to see if I can look at this. Yeah, it looks like it's coming through on the board okay. All right. So what do we know? We have to pick some quantity. We have to pick some quantity. So what we know about 16.0 molar nitric acid is that if we have 1 liter of solution, we have 16.0 moles of nitric acid in it. That's how molarity is defined. moles of solute, nitric acid, per liter solution. So for every, let me change this a little bit. So let's see, we have grams, moles, and we have volume, liters or milliliters. And by the way, you should be able to do that conversion so quickly in your head, it'll make you blind. All right, so solution. I know that I have 16.0 moles of my solute in every 1 liter of solution. Or in 1,000 mils. That's my starting point. So how do I move around on this table? I know moles. If I need grams, I can go from moles to grams. If I know grams, I can go from grams to moles by the molar mass. For the solution, remember that the solution is this plus this. It's these two added together to give this. I don't know this, I don't know this, I don't know any of these to start with. When you're given the density, I just mentioned that the density only applies to the solution. That's this right here. That means that for every 1 milliliter of solution, it has a mass of 1.51 grams. For every 1 mil of solution, it has a mass of 1.51 grams. So if we have 1,000 mils, that means the mass of my solution is 1,510 grams. See that? You can do the calculation if you need to by dimensional analysis. 1,000 mils solution times 1.51 grams divided by 1.00 ml of solution. And we get this. Okay, I'll assume that you're with me at this point. We have everything we need to find out everything else. What are we trying to find? We're trying to find molality, mass percent, and mole fraction. So let's go ahead and find them. Let's start with molality, since that happens to be listed first. For molality, I am looking for moles of HNO3 over kilograms of my solvent, which is H2O. Well, I already know the number of moles of my solute. That's 16.0. That's the same. Notice in those concentration units, 3 of them have the same numerator, moles of solute. Now, I want to find this number right here. I need to know how many kilograms of water I have. I know how many grams of solution. I need to know how many grams of these two, because I know that the mass of each of these two added together gives us 1510, mass of our solution. Remember, solute plus solvent equals solution. All right. HNO3. Well, we need to find the molar mass. H, N, and O. 1 hydrogen, atomic mass of 1. 1 nitrogen, atomic mass of 14. You've all got the periodic table memorized, right? Perfect, lovely. And each oxygen is 16. 16 times 3 is 48. So I add these together, and I get 63. So now what I need to do is whip my sophisticated calculator and convert moles to grams. That would be 16 times 63, 10,008, 1,008, 1008. Are my sig figs correct? Do they matter? Yeah, close enough. All right. Now, remember that this mass plus this mass equals 1510. So this number, the difference between these two, has to be 502 grams. Got this? Questions? I thought I heard a question in the back. No, I must have been dreaming. Just another voice inside my head. All right, but now I know that this number goes right here for kilograms. So this is now, see, I'm not sure if you can see it. I'm going to move it over just a little bit. This is equal to 16.0 moles of HNO3 all over 0.502 kilograms. Because you know your metric prefixes, you know immediately that 502 grams is 0.502 kilograms. All right. Just make sure that you're seeing that. Yep, great. Okay. So now we know the molality. 31.9, I think. Let's see, 16 divided by 0.502, 31.9. And that is molal HNO3. All right. That is molality. Let's do mass percent. Mass percent, grams of solute divided by grams of solution times 100%. It's this divided by this times 100. So this is 1008 divided by 1510. 0.6675 or 66.8%. HNO3. Notice that I'm writing out the unit each time. Lastly, mole fraction. Mole fraction. Mole fraction, remember it's a fraction, not a percent. It's moles of solute over total moles. It's moles of solute divided by total moles. I need to know the number of moles of my solvent. So I go 502 grams, and my solvent is water. Remember all this from Gen Chem 1? Grams to moles, conversions, atomic or molar mass, atomic mass stuff. So 502 divided by 18, 27.9. So I know the moles of HNO3, my solute. I know the moles of water, my solvent. Together, we get 43.9 total moles. In order to calculate mole fraction, this is 16.0 moles of HNO3 all over 43.9 total moles, not times 100, and I get, let's see, 16 divided by 43.9, 0.364. That is the mole fraction of HNO3. See, it's easy. Not a problem at all. All right, so if you haven't already, I hope that you've written this down. I hope you've been able to follow what I've done. Notice what we were given. We were given molarity, and we were given density. The density only applies to the solution. It only gets us from here to here and back. Mass to volume of solution, that's density. Solution only. Here we started with 16 molar. That means that for every liter, we have that many moles. I could start with molality. I could have started with a number of different things. It just depends on where we plug stuff in to the table. All right, now, I'm going to set this up for you. This is worksheet 1. So this would be a perfect time for you to go, download it, print it, or if you're not able to print it, it's easy enough to copy, and copy on a piece of notebook paper. All right, so we have a solution. The solution is 60% sulfuric acid by mass. It has a density of 1.49 grams per mil. Determine molarity, molality, and mole fraction. What's different here? I'm given mass percent, not molarity. I'm still given the density, but I'm given a different starting concentration. Okay, so I'm going to go through and work through setting up this the same way I did last time. So this is going to be grams of H2SO4, sulfuric acid. It's going to be grams of H2O, and this is going to, I'm sorry, those aren't grams. It's been a long day, folks. And I know that despite how amazing and thrilling this video is, I apologize, there's still something to be desired. All right, here we go. Same thing, we have grams, moles, and volume. But keep in mind, for volume, we're never going to have anything for our solute volume because it's usually going to be a solid. Typically, it's a solid. At least anything that I'm going to give you is going to be a solid or, so let's call it not a liquid. I'm not going to need to use a liquid. All right. Now we need a starting point. We know that 1.49 grams per mil, that's our conversion between mass and volume of our solution only. Then we've got 60% sulfuric acid. Now, there are a couple of different ways of working this. I prefer to start with 60% sulfuric acid because this is what I'm given. But basically what we need to do is choose some quantity. We can choose any quantity. I could choose 100 grams. I could choose 100 grams because if I have 100 grams of solution, if this is 100 grams of solution, then 60 of that 100 grams is H2SO4, and 40 of those grams are water. So that's one way we can start this. If you want to work this that's very, very similar to what I did last time, we could take a liter of solution. Let's pick 1 liter of solution. If I take 1 liter of solution, so I'm not trying to be confusing, that's why I want to try to be consistent with what we did on the last problem. It doesn't matter which quantity you pick. What matters is that everything is proportional along the way. That this is proportional to this, which is proportional to this. That's what matters. So here's what a lot of my students in the face-to-face class did. They said, all right, let's say that we have 1,000 milliliters of solution. And if we have 1,000 milliliters of solution, that's a great starting point. How much does this, what's our mass? What's our mass here? 1,490. If this is our total mass. If this is our total mass, 60% of this is the mass of H2SO4. So what is 60% of that? 1490 times 0.6. 894. 894 grams. This number is the difference between these two. $596. Okay. Now I've got mass. And I've got the volume of solution, and I've got the mass of the solution. So I've got a lot of things that I already need to do these calculations. So if I need to find moles, I can go from grams to moles for H2SO4. If I need to find moles, I can go from grams to moles for H2SO4. So I need to find the molar mass of this. Find the molar mass of H2SO4. Hydrogen is 1, sulfur is 32.06, oxygen is 16.0. The molar mass is somewhere around, it's 32 and 64, that's 96, 97, 98, right around 98 grams per mole. Right around 98, 99 grams per mole. Water is 18 grams per mole. I can find the number of moles. So if I know the moles here, I can find the total moles. This divided by total moles is mole fraction. Percent composition, well, I already know it's 60%. That's how I got these proportions. If I want to find molarity, it's moles of solute divided by liter solution. So it's this number divided by 1.000. If I want to find molality, molality is moles of solute divided by kilograms solvent, 0.596. All right, so I've taken quite a bit of time to walk through the first part of chapter 13. I'm going to stop this now and upload, try to get this uploaded to Moodle before the end of the day. All right, we will talk to you again on Friday, folks.